Hello student. So in our last class we have discussed the row reduced echelon matrix. So I think you can recall what are the property in the row reduced echelon matrix, right? Now similar thing for column reduced echelon matrix also. Okay, I'm just let down the property of column echelon matrix. Okay, so a matrix is said to be your column equivalent or CREF if it is column echelon form. Okay, and each pivot is your one, and so basically whenever your column echelon form, they are actually that this type of property. Like in row, you know, all the zero entry in the lower portion of the matrix, right? So similarly, whenever you have column echelon matrix, basically all the zero column you will see here. Okay, this type of property is there. And if suppose you have some element here, so all the other element will be zero in your you can say the left right of that pivot element. Okay, like that. Okay, same thing, just here this is, you can say, like vertically, and CREF is like your horizontally, right? Okay, so each pivot is equal to 1, and each pivot is the only non-zero entry in its it will be a row, right? Okay, and zero rows are always on the right, that is in your column equivalent form. So you can say, if you have one minute example, so if you have 1 0 2 0 1 3 0 0 0, so this type of matrix you can say, and this is column echelon, column reduced echelon form also. Okay, because this is your that pivotal element here. Okay, and next is your this one, and you see this type of element are zero, right? So no issue there. Okay, next, so next we'll discuss the rank of a matrix. So what is a rank of matrix? Rank of matrix, you can say, if you have find the corresponding row echelon form or row reduced echelon form, anything, so there the number of non-zero row is actually give the rank of a matrix. Okay, so rank of a matrix is the number of non-zero rows in row echelon form in its row echelon form. Okay, this type of thing. Okay. And in case of column equivalent form, you will see a number of a non-zero column. Okay. So for a matrix that will be unique. Okay, so that it is not that if you do row operation, then you obtain a row equivalent form, there the rank you are getting 2, and if you do the column equivalent form, that will be 3. That is not true. Okay, so actually, if you do that row operation or column operation, the rank of the matrix is not changed. Okay, so I think earlier also we have discussed some operation. For example, if you see this one, you have, this is your A. After that you have apply some row operation and you have converted into RREF, right, row reduced equivalent form. If you convert in just row equivalent form, that is also possible. Okay, no problem for that. Okay, so how many non-zero row here? This one and this one, so you have 2, right? Okay, let's copy this one. Copy. Okay, so the rank of A is your 2. Okay. Okay, there is other definition also, that some books written that rank of a matrix is actually the number of pivot element in your RREF, right? Because you see these are actually your pivot element, right? So because each non-zero row you have a pivot element. Okay, so this is also true. So you can just write some remark. A rank of a matrix a number of pivot element in echelon form. Okay, there is another concept I think you have done in your class 12 level, and that whenever you have some matrix, you can find the corresponding minor of that matrix, right? Minor, cofactor, that type of thing you have learned earlier. Okay, so basically rank of the largest order non-zero rank is the largest order non-zero minor. Okay, so largest order. Okay, so for example, if you consider this A, okay, what is this A element? Okay, this is a matrix. So if you say third order minor, okay, third order minor, so that means it will be a whole matrix, right? Third order, that means 3 cross 3. So if you find its determinant, you just check what should be the determinant of that. So it is actually non-zero in the sense of determinant. Okay, that if you do find a determinant, that will be non-zero. Okay, so 1 into 4 plus 5 minus 2 into 8 plus 1 plus 1 into 10 minus 1. So what are you getting? 9 minus 18 plus 9. You see, you are getting 0. So third order minor is actually 0. Okay, now if you consider second order minor, you have to, so whenever you are finding the second order minor, so there is actually 9 such minor, right? For example, for this 1, if you find this, so you have this type of thing, right? For 2, if you find, so you have this type of matrix, right? For this one, if you find, so you have this type of. So the thing is, you will find at least one of them whose determinant should be non-zero. So you see, if you consider this only, for example, for this element 4, so what should be the determinant? 1 into 1 minus 2 into 2, so this is minus 3, non-zero element. So you are getting a second order minor whose determinant is non-zero. So you can say, so what is the highest order? Obviously 2, right? So from there you can say its rank is your 2. Okay, like that. For example, in case of, suppose you have 2 order some matrix. Okay, suppose 1 3 4 5, like that. So if you find its determinant, okay, so determinant is your 5 minus 3 into 4, so that is minus 7. Okay, so this is non-zero element. So this is a second order minor whose determinant is non-zero. So you can say easily its rank will be 2. Okay, this type of thing. For example, if you write one more thing, suppose 1 3 to 6. Okay, this type of matrix. So what is the determinant here? So 6 minus 6, that is 0. So rank is 2 is not possible, because 2 order minor is not non-zero, or that is 0, right? So you have to consider for 1 order. You see, 1 order means single element. Obviously in that matrix not all element are 0, right? So you can say for this matrix the rank will be the 1. Okay, you can check if you convert into its corresponding equivalent form. So obviously you will get 1 3 0 0. So you have the number of non-zero rows is 1. So from there you have that its rank will be 1. Okay, so this type of concept is required. Okay, now whenever you will learn the vector spaces, maybe in upcoming semester, then you will learn more that some your linear combination of your row, that type of thing is called row space. So dimension of row space is actually rank. So similar, the linear combination of column forms the column space. Okay, and the dimension of that is actually the also the rank. Okay, so that type of thing we'll discuss later. Okay, okay, now that normal form of matrix. Okay, so what is this normal form? Basically every matrix of rank R can be reduced by row and column column operation to the form IR 0 0 0. Okay, this type of thing. Okay, so these are element are actually whole zero. This is like some zero order block. You can find a block. Okay, so every matrix of rank 2 can be reduced by a row and column operation. You can first you apply your row operation and then try for your column operation. Okay, you will get that one. For example, already we have done this thing, right? One of the problem that I check. So this matrix you can convert in this form. So from here, how to convert this into that form? You just see, if you do one more operation like R1 dash will be R1 no, that is not true. Basically after that, if you do some row operation, you will not form the in that normal form, right? So basically what you will do, first you will try to convert into its RREF, then you apply the column operation. Okay, so in this way you can able to form in the normal form. So what operation you should apply? So you see, if we apply that C3 C1 C3 dash equal to C3 plus C1 minus C2. Okay, this type of operation I am doing. Here I am applying two operation together. You can do one by one also. Basically remember, whenever you are doing the operation, I told you earlier also, whatever the operation you are starting, that this thing will be same. After that, whatever you will do, you apply. After that, plus with some constant multiplication, that type of thing. You see, you should get I2 0 0 0 0, right? This type of thing. So you are getting this type of block. So this matrix is converted in the corresponding normal form, right? Okay. So what is the extra in your normal form? So normal form, it is more clear, right? IR. So basically basically this is like 1001. So it is more clear that there is actually two pivot elements. So for R it is you have R pivotal element. Okay, and if you think from your that minor point of view also, you will get the R order maximum non-zero minor, right? So this type of thing is you can have. So you just try a homework. So already we have give you homework. You just try this problem. You try to convert in its normal form. Okay. Next you have a congruence operation and congruence matrix, right? What is in your syllabus? Yeah, congruence operation and congruence matrix. So congruence operation is, suppose you have a matrix A and P be a non-singular matrix. Okay, let P be a non-singular. Remember, whenever you have some non-singular matrix, that means it's have full rank, right? Because when a matrix is said non-singular, that means its determinant is your non-zero, right? So that means it has the highest order minor, that is basically if it is n cross n, so you can say your its rank is n, right? Okay, let P be a non-singular matrix. Then B equal to P transpose AP. Okay, this is this type of operation if you apply on that A, so this type of thing is called congruence operands, or you can say A and B is congruent. Okay, say A and B is congruent. Okay, remember this congruence also preserves its rank. Okay, it's preserve okay. Next, okay. Now after that there are only two more thing. You also check your previous year question also. Okay, uh, what are the question is coming. I have not seen no question is coming from this congruent type of thing. Most of them are actually from your or rank, convert into normal form, or you're solving a linear equation, this type of thing. You also check, and if you have any problem, you just send me in the WhatsApp. Okay. Okay, so next is your signature signature and index. Okay, so what is happening, you see, if you apply your row and column together, you can convert into this type of ir comma 0 0 0 this form. Okay, that is fine, but whenever you are applying the row operation, okay, row operation, after that you are using the column operation, right? So I think earlier you have seen in the product of row, what is this type of thing is called, forget that, eij type of thing, right? I have written earlier that you are multiplying with some, you have some matrix A, and then you are applying with P, right, where P is actually some product of eij, that E type of matrix. Okay, and if you have some doing, after that you are doing some column operation, that will be from the right side, so that will be on the PAQ type, right? But here in the congruence operator you are not doing that Q. Okay, here you are multiplying with the same thing with some transpose. Okay, so if you apply this type of thing, you will get some 1 minus 1 and 0 combination diagonal matrix. Okay, so I am writing the theorem that is actually called the law of inertia. Okay, that every definitely this is not for all matrix, every real symmetric matrix A, you know what do you mean by symmetric? That A transpose equal to A, right? And this is real. Okay, that is each element are real. Okay, a symmetric real matrix A is congruent to a diagonal matrix DAG 1 1 dot 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 1. You have suppose P such one. Okay, and then you have minus 1 dot 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 minus 1, that is suppose Q times, then you have 0 0 0. Okay, so this type of thing. Okay, so basically what do you mean by this diagonal? Basically here you have 1 1 1, or basically you can say IP, right? It will be more better. IP is here, then you have minus IQ, and then you have some 0, this type of thing. This diagonal matrix looks like that. Okay, so law of inertia says you can able to find some P for which that P transpose AP will be of that form. Okay, now if you have this type of thing, now after that your so P is the number of positive one, Q is the number of negative diagonal entries, right? So you can say P is the number of positive diagonal entry, right? And Q is the number of negative diagonal entry, right? Okay, so then signature is defined as will be P minus Q. Okay, and the index is actually the number of negative entries, so index is your Q. Okay, okay, so this type of thing is there. For example, suppose you have a matrix A. Okay, and A is congruent to suppose you have 1 1 minus 1 minus 1 minus 1 0. I have written this type of element, all other element is 0. So from there you can say what is the signature? Signature is your actually 2 minus 3, right? This is your minus 1. And what is your index? Index is actually your 3, right? And what is your rank? Rank you can say 2 plus 3, right? So 5, because 5 non-zero, this type of thing. Okay, so okay, in some book there is some notation, forgot where it is. I have seen that, let me check. Yeah, signature is notation is just small s. Okay, this type of thing. Sorry, this index is actually the number of positive entry. Okay, so this is actually p, it will be. Okay, so index will be here 2. Okay, fine. So this is completed. One thing is there, that is the solving the system of linear equation in matrix method. Okay, so what are the thing? So already I think the first class I show you, right? So what you have to do, suppose you have a system a11 x1 plus dot 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 a1n xn equal to suppose b1. Okay, in similar way you have an1 x1 plus dot dot dot, you have ann, and it should be better if I write m. This is your mn, xn is your bm, right? So you have this matrix in the form of ax equal to b, right? This thing already we have discussed, where x is your n cross 1 matrix, this is your m cross n matrix, so this is your m cross 1 matrix, right? Okay, fine. So this type of matrix. So after that, there you have the augmented matrix. Okay, augmented matrix. What is augmented matrix? Augmented matrix is, you have to write a and you will write the b with that. Okay, it will be better if I write the, okay, capital no issue. Some book they are write with small notation. Okay, if you write that small, so yeah, you can write this is your x, this should be in your b, so this is the thing. Okay, so you will do your row operation here, okay, in the AB form. So after that you will get some easier matrix, right? You know, whenever you have this matrix, from there you can convert into the system of equation, and if you have system of equation you can convert into the augmented matrix. Okay, so from there you can easily find what are the solution. Okay, now there is a let's try one problem. For example, if you have x plus y plus z equal to 6, 2x plus y plus 3z equal to 14, and you have x plus 2y plus 2z equal to 10, suppose. Okay, so if you find the augmented matrix here, okay, augmented matrix, you have 1 1 1 2 1 3 1 2 2, then you have 6 14 10, right? This type of matrix. Now it is your job. Okay, you apply some row operation. You don't think there is some border. Okay, you just use your row operation, that's it. You just think this is your 4 cross 3 matrix, sorry, number of rows 3, so 3 cross 4 matrix. Okay, you just apply your row operation and convert into this type of form, 1 0 0 0 1 0 0 0 1. For this matrix I am getting this, I am taking this from the book. Okay, so if you have this type of system, so obviously from there you have x is equal to 2, y is equal to 3, and z is equal to 1, right? So this is the system. Okay, this is the technique. Okay, Now there is a some condition when you have unique solution, when you have infinite solution, when you have no solution. I am writing this thing. This is very important. So basically you see, if you have 0 row here, okay, so then what you will get? You will get actually z is unknown, right? Z can be anything, so then you have infinitely many solution. Okay, so I am writing the the system is consistent if the rank of AB, that is augmented matrix, is equal to the rank of A. Okay, and if you have the system is consistent if your rank of AB equal to rank A. Okay, now what's happened if your rank of A is also the full rank? Okay, so if your A is suppose n cross n matrix, okay, and if you have this is equal to the full rank, then it has unique solution. Okay, okay, this is the system. 1 minute, let me write. Is consistent means it has some solution. The solution may be unique, may be infinite. Okay, and no solution if a rank of AB is not equal to rank of A. Okay, now I am considering the case, suppose your A be a n cross n matrix. Okay, then it has, you can say this is your case 1. Okay, this is your 1, this is your 2. Okay, now in the case of 1 A, I am writing that is the system is consistent, and under that you are doing A, that it has unique solution if a rank of AB equal to rank of A equal to n. Okay, and 1B is it has infinitely many solution if your rank of sorry, this is equal to, right, rank of A, this is strictly less than A, then it has infinitely many solutions. Okay, so this thing you have to remember. Okay, so this is the problem I am giving you to solve some problem. You just try this one. Okay, that suppose you have okay, homework 3x1 plus 2x2 plus 3x3 minus 2x4, this is equal to 1. You have x1 plus x2 plus x3, this is will be 3, and x1 plus 2x2 plus x3 minus x4 equal to 2. Okay, this is the this problem you just try. Okay, so this is the matrix theory thing. The first portion is this one. In next class, I will discuss the matrix eigenvalue, eigenvector, that portion. Okay, and there after that we will discuss some problem from your PYQ. Okay, one more class is enough for your unit 5. Okay, so then we'll discuss some PYQ. Okay, that's it. Okay, bye for today. You try your homework and send me in WhatsApp. Okay, I appreciate whoever sent me the homework, but very few. It is not expected.